This is your presenter, Asloop Mudassar, and I am presenting slide number 17C of the course on atomic and molecular physics. In the today's lecture, I shall be covering hyperfine structure in external magnetic field, electron spin resonance. This is a third lecture of the series on hyperfine structure. Hyperfine structure in an external magnetic field and electron spin resonance. External magnetic field B naught, when applied, it adds to the internal magnetic field Bj. I have defined Bj in the last two lectures. If B naught, which is the applied magnetic field, has a magnitude which is much less than Bj, then the magnetic potential energy due to B naught is small compared to energetic separation of hyperfine terms. One speaks of the Zeeman effect of the hyperfine structure. I and J couples to form capital F, which is the total angular momentum of the atom in the presence of the nuclear spin. So you see that here I am talking about Vj due to magnetic field B naught. Since B naught is much smaller than Bj, so this quantity, which is B magnetic B naught, is small compared to the separation between the hyperfine terms. If this is small, then one can speak of the Zeeman effect of the hyperfine structure. And in the Zeeman effect, both quantities I, that is the nuclear spin, and J, that is the total angular momentum of the electrons, these two quantities couples together to form the total angular momentum F of the atom. If B naught is strong enough, the coupling between I and J breaks down, and one talks about the push and back effect of the hyperfine structure. You know that when I am talking about hyperfine structure, it means that I am taking into account the nuclear spin. So if B naught is strong enough such that the coupling between I, that is the nuclear spin, and J, which is the total angular momentum of the electron, breaks down, and then one talks about the push and back effect of the hyperfine structure. The transition from Zeeman to push and back effect occurs at much smaller fields than required in case of the fine structure, due to small splitting magnitudes involved in hyperfine splitting. So you see that in hyperfine splitting, the quantity I, which is the spin, nuclear spin, is a very small quantity. And to break down the relationship between I and J, a small amount of magnetic field is required. Smaller in comparison with the magnetic field required for the fine structure to be converted into for the fine structure. So the magnetic field that is required in the fine structure is much greater as compared to the field required to observe the hyperfine splitting. In hyperfine structure, the magnitude of B naught may be of the order of 0.1 Tesla. And if B naught is of this order, then it is assumed a strong field. So you see that in order to observe the hyperfine structure, a magnitude of the applied external magnetic field, if it is of the order of 0.1 Tesla, then it is assumed a strong magnetic field. Hyperfine Zeeman structure. And you know that when we are talking about the Zeeman structure, it means that we are talking about the weak magnetic field. That is, the external magnetic field is weak in the presence of the nuclear spin. So we are taking into account the nuclear spin. That is why I am talking about a hyperfine structure. And Zeeman mean that the magnitude of the magnetic field is weak. That's why I am talking about here hyperfine Zeeman structure. So hyperfine Zeeman structure in graphical form is shown on the next page. So let me show that one that you first. This is, you can see Zeeman effect. And you know that in the Zeeman effect, I have the quantities I is the nuclear spin, J is the total angular momentum due to electrons. I will carry out a precessional motion about F. You know that I and J, as you see, I have shown a vectorial addition of I and J. When they add together, you will get a total quantity, total angular momentum of the atom as a quantity F. So I will carry out, I, which is the nuclear spin, will carry out a precessional motion about F, and similarly J will carry out a precessional motion about F. I will carry out a precessional motion with its vector tip tracing the blue loop, whereas J will carry out its precessional motion following the red loop. And then F, the resultant of I and J, will carry out a precessional motion about the green loop about the external magnetic field B naught, and B naught and Z have the same direction. The magnitude, the Z component of F is also shown as a projection of F onto the magnetic field B naught. There are two components of F which are Fx and Fy. These two components will average out to zero during the precessional motion, and only one quantity can be measured, which is the Fz component of the vector F. So this is the picture of the Zeeman effect, hyperfine Zeeman effect. Because hyperfine means in the sense that I am taking into account the nuclear spin. So if you take into the nuclear spin into consideration, then this is called hyperfine Zeeman effect. And the Zeeman effect means that the magnitude of the magnetic field B is weak, so that there is still a coupling between I and J, and I and J couples together to form the total angular momentum F of the atom. And F, then in the presence of the applied magnetic field B naught, will carry out a precessional motion, and only the Fz component of the vector F will be measurable. Hyperfine Zeeman structure in graphical form is shown on the next page, which I have briefly explained. Total F is composed of angular momenta I and J, because I and J will add vectorially to give you the total angular momentum capital F of the atom in the presence of the nuclear spin. Both I and J precess about F, and F precesses about B naught. Only the Z component of the vector F will be observable, which is the projection of vector F onto the magnetic field axis or onto the Z axis. Precession frequency of I and J about F is much higher than the precessional frequency of F about B naught. So this is an experimental effect that have been observed, that is I and J will carry out a precessional motion about F with a very high precessional frequency, but the F will carry out a precessional motion about P naught with a lower frequency. So F has how many orientations of the vector F will have about the magnetic field B naught? There will be F plus 1 orientations of capital vector F about the magnetic field B naught, which are given by the quantum number MF. So MF is actually the magnetic quantum number due to the vector F. So MF may be regarded as the total magnetic quantum number due to the spinning of the total angular momentum F of the atom, which precesses or spins about the magnetic field B naught. So M is actually the magnetic quantum number, and this has the same number of orientations, that is 2F plus 1. So MF will have 2F plus 1 values. And you know that MF will exist only under the application of the applied magnetic field B naught, in which case F will carry out a precessional motion about B naught. If there is no B naught, there is no precessional motion of F about B naught, and there is no magnetic quantum number MF. So here I am writing down an expression for the Z component of vector F. So Fz is equal to Z component of vector F, which is equal to MF into H bar. Such relations that is about the Z component, I have been writing such relations for the atomic quantities in previous lectures. So you can consult those lectures and also the last two lectures of this series. So I have Fz is equal to Mf into H bar, where Mf has a value equal to F minus 1, F minus 2, and so on up minus F. But if f is an integer, then you can include the zero value in that. So in that case, if mf is an integer, then mf will be equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on up to plus minus f. But if mf is a fraction, then it will have the values f minus 1, f minus 2, and so on up to minus f. And for optical transitions, the selection rules are delta f is equal to 0 plus minus 1, and delta mf is equal to 0 plus minus 1. So delta f and delta mf will obey similar rules, similar selection rules for the optical transitions. And I shall be talking about them in greater detail when I shall discuss some spectra. So hyperfine Zeeman splitting is given by this is you see that hyperfine Zeeman splitting I am talking about. And you know that when I am talking about Zeeman splitting, but I am talking the word hyperfine along with that, it means that I am taking into account the nuclear spin I. That's why it is called hyperfine. So hyperfine Zeeman splitting is given by VHF, that is the magnetic field due to hyperfine structure, is equal to minus the dot product of mu f and b, where b naught is the external magnetic field, and mf can be written as mf is equal to mj plus mu j and mu I. So mu f can be written as mu j plus mu I, where mu j is the electronic magnetic moment, that is the magnetic moment due to the electronic contributions or due to the contributions of the electron, and mu I is actually the spin magnetic moment. If I am talking about the hydrogen atom, for example, then the mu I will be the magnetic moment of the proton. Atomic terms undergoing Zeeman hyperfine splitting is given by. So you see that I am now here giving out to you the Zeeman hyperfine splitting energy, which is delta EHFS is equal to GF into mu B into B naught into MF. Since I am considering over here delta E, you may consider it as delta F. Or otherwise you can remove the delta sign over here and you can simply write EHFS is equal to GF into mu B into B naught into MF. And if you are considering a change in energy between the two consecutive hyperfine Zeeman hyperfine levels, then you can set MF is equal to 1. But if you are considering delta E between two levels which are not consecutive, then you can write delta E HFS is equal to GF into mu B into B naught into delta MF. So this MF can be converted into delta MF for more precise equation. The value of GF, this G factor for the corresponding to the vector F has the expression which I have given over here. You know that these expressions have been derived using the quantum mechanical approaches, and I am only borrowing those results from such calculations. If I repeat those calculations over here, then of course I would spend whole of my time on one chapter. So just I am borrowing some useful results from the other calculations, probably done using quantum mechanical approaches. So here GF is equal to GJ, and then we have f into f plus 1 plus j into j plus 1 minus I into I plus 1 divided by 2 times into f plus f1, and then I have minus gi multiplied by the ratio of mu n to mu b, that is the ratio of the nuclear magneton to the Bohr magneton, and then multiplied factor multiplied by the term f into f plus 1 plus I into I plus 1 minus j into j plus 1 divided by 2 into f plus f1. Now the ratio of mu n to mu b, that is the ratio of the nuclear magneton to the Bohr magneton, is 1 over 1836 for the case for example hydrogen atom. So due to this small quantity, the second term in equation number 36 can be dropped or neglected. There are two F plus 1 equidistant components under weak magnetic field as shown in the figure below. So you see that this is the figure that I am considering over here. And this is the electronic state 2s1 half. And this 1 half in the electronic state is actually the value of the j vector, value of j. That is the value of the total quantum number of the electronic system. J is equal to half in this case, and I is equal to half, I is equal to 1. So I am considering an atom for which the value of I is equal to 1. That is the value of the nuclear spin is 1. So now I have two values, J is equal to half and I is equal to 1. And you know that F is given by the mod of I plus minus J. I is 1 plus minus j, j is half. So I plus half is equal to 3 by 2 and I minus half is equal to 1 by 2. So there are two values of f. F is equal to 3 by 2 and f is equal to 1 by 2. And you know that this dotted line is the reference line corresponding to the level given over here. That is the 2s half level. So this dotted line is an extension of that level. And with so the f is equal to 3 by 2 level exists a by 2 above the reference level, and the level f is equal to half exists 3a by 2 below the reference level. And these levels, these values, that is a by 2 and 3a by 2, can be calculated from the expressions that I have discussed before. So you can put the values of j is equal to half, the value of I is equal to 1, and the value of f is equal to 3 by 2. Then you can calculate this splitting interval, which is equal to a by 2. Similarly, putting the value of j is equal to half, I is equal to 1, and f is equal to half, you will get the interval is equal to 3a by 2. So you see that these are the values of f under the condition when the magnetic field is not present. Now let's apply the magnetic field. When you apply the magnetic field, then of course the F levels, the F level will split into MF levels. And you know that MF is regarded as the magnetic quantum number, MF. So since F is equal to 3 by 2, MF will be plus minus 3 by 2 and plus minus half. And you know that I have arranged them in the order of energy. Plus 3 half has the maximum energy, then plus 1 half, then minus 1 half, and then minus 3 by 2. So these are the quantum numbers, MF quantum numbers, and I have arranged the four levels due to F is equal to 3 by 2 under the application of the moderate magnetic field B naught. This F level which is a degenerate level, will split into MF levels. So I have shown four levels corresponding to F is equal to 3 by 2. Similarly, under the application of the applied magnetic field, which is the moderate magnetic field, or you can say that it is a weak magnetic field B naught, the level F is equal to half, which is a degenerate level, will split into two levels according to the value of MF, which are plus minus half. So I have arranged them in the values of energy. So MF is equal to minus 1 half lies above the MF is equal to plus half in energies. So I have shown all these four levels. So all these six levels, four levels corresponding to F is equal to 3 by 2, and the two levels corresponding to F is equal to half, these are the Zeeman levels. Or you can say that since I am including the nuclear spin also over here, you can say that these are the hyperfine Zeeman levels. But you know that if the magnetic field is strong, or you apply or you convert or you make this magnetic field to be stronger, then what will happen? This is what happen, which I have written on the right hand side of this. So the number of levels will remain the same, but you know that they will be distributed with different energies. That is, the partition between these levels will be different. So then you see that the splitting of these level will depend upon two quantum numbers, Mi, which is the magnetic quantum number due to nuclear spin, and Mj, which is the magnetic quantum number due to electronic angular momentum. So you see that consider the value of j over here, which is half. From 2 as half, you can infer the value of j is half. So mj which is equal to plus minus half. So you see that I have written mj is equal to plus half at the top and minus half at the lower levels. Now mi, here I is equal to 1. When I is equal to 1, mi will have levels 0 plus minus 1. Because mi will have values 0 plus minus 1 plus minus 2 plus minus 3 and so on up to plus minus I. Since I is equal to 1, so the maximum value will be equal to 0 and plus minus 1. So mi has three values, plus 1, 0, minus 1. And similarly for the lower levels, I have values minus 1, 0 and plus 1. And I have written lower values in the order of energy distribution. So this plus 3 by 2 will appear with across the two values of mi and mj, which are plus 1 and plus half. Similarly, plus half level will appear corresponding to mi is equal to 0 and minus and f is equal to minus half level of the hyperfine Zeeman splitting will be written as minus 1 with mf with mi is equal to minus 1 and mj is equal to plus half. And these levels which I have shown over here with the strong magnetic field, these are actually the hyperfine structure levels. But what hyperfine? Push and back. So these are the same number of levels as the hyperfine Zeeman effect, and these are the levels which are the hyperfine push and back due to push and back effect. And you know that in the push and back effect, the energies of these levels will be determined by the quantum numbers mi and mj, which I have explained and I have written against each level. So let me start with this one. 2s half, no magnetic field. When you apply the when there is no magnetic field, this level, due in the presence of the nuclear spin, that is due to the hyperfine structure, I will couple with J and you will have two levels, F is equal to 3 by 2 and F is equal to half. And this is the hyperfine structure. But when you apply moderate or weak magnetic field, then these levels will be hyperfine Zeeman levels. And when you apply the stronger magnetic field, then you will get the same number of levels, and these levels will be called as hyperfine push and back levels because these arise due to push and back effect. So you see that I have simply explained the F levels, which are simply the hyperfine levels. Then I have explained these levels, which are the hyperfine Zeeman levels, and then I have explained these levels, which are the hyperfine push and back levels. When V naught is increased, that is, you make the beam stronger, you make the applied magnetic field to be stronger, then of course the push and back effect will take place. And I and J will decouple. That is, the coupling between I and J will break down, and there will be no value of the total angular momentum F of the atom. In the case of Zeeman effect, you have the total angular momentum F, and of course the corresponding magnetic quantum number mf in the presence of the magnetic field, weak magnetic field. But when the weak magnetic field is much stronger, I and J will dissociate. That is, there will be no coupling between the spin angular momentum I and the electronic angular momentum J. These two quantities would not be able to couple with each other, and the decoupling will occur. And you know that if I am talking about the LS coupling for the electronic spectra, not including the nuclear spectra, then of course you see that in that spectra I have discussed the LS coupling becomes stronger due to the interaction of mu L and mu S coupling. The source of you see that this line, which is LS coupling, becomes stronger due to mu L and mu S coupling. This will only be applicable when the nuclear spin is not taken into account, and we are simply talking about the LS coupling without nuclear spin considerations. But since here in this chapter I am considering the nuclear spin, that is, I am considering the hyperfine structure. So the source of this nuclear spin I and the electronic spin or the electronic angular momentum J coupling is due to, that is, the coupling between I and J was due to mu J, which is the electronic magnetic moment, and a much weaker nuclear magnetic moment mu I. So mu J and mu I couples. Then due to that coupling, I and J couples, and then the resultant quantity capital F is formed. And then, of course, we talk about the hyperfine Z-main effect under the application of weak magnetic field. So under the application of a weak magnetic field, mu J and mu I couple together, and as a result, I and J couples, and then a total angular momentum F of the atom is formed, and then we can talk about the hyperfine Z-main effect, because the vector F will then carry out a precessional motion about the applied magnetic field B naught. So you see that this is the picture that I am going to show you over here, is the picture which corresponds to the push and back effect. That is when the magnetic field is strong and that there is no coupling between I and J. So you see that in this figure, you can see that I and J are independently carrying out a precessional motion about the external magnetic field B naught. So I carries out a precessional motion about B naught, and only its, if you want to measure its component, only the IZ component will be measurable, because the other two components, which are IX and IY components, they will average out to zero. Similarly, you can see over here J vector, which is also independently carrying out a precessional motion about the magnetic field B naught, and its Z component, which is Jz, can only be is the only component that can be measured. The other two components, Jx and Jy, will be averaged out to zero during the precessional motion of J about B naught. So this figure is relevant to the push and back effect, or to the effect when a magnetic field B naught lies in the strong range. So we are here considering stronger magnetic field. J precesses about B naught. The magnitude of the electronic field at the nucleus, which is the Bj, which is the magnetic field due to the electronic shells. This field Bj is due to the electronic shells at the nucleus, has a magnitude of 10 to 100 Tesla. And Bj is usually much greater than B naught. I is expected to oscillate or precess about J, but since the precession of J about B naught is very rapid, nuclear moment mu I experiences a constant component of Bj in the direction of B naught. So you see that under this condition, when the magnetic field B naught is much stronger, then then Bj will also be aligned along the magnetic field B naught, and mu I, which is the nuclear magnetic moment, will also be aligned along the magnetic field B naught. So mu I experiences a constant component of a Bj in the direction of a B naught. The precession frequencies of I and J about B naught are, however, different. So you see that, as I explained, J and I will carry out independent precessional motion about B naught with different frequencies. In the hyperfine structure of push and back effect, which we are currently discussing, F is not defined. Graphical representation is shown over here, which I have explained you. That is, here there is no quantity like F, because J and I are decoupled due to the strong magnetic field, and they are carrying out a precessional motion independently with different frequencies about the magnetic field B naught. The Mi and Mj associated with I and J will be valid. the splitting energy of the atomic terms will be. You see that Mi is the magnetic quantum number associated with the nuclear spin, and Mj is the magnetic quantum number associated with the angular momentum J of the electrons. So Mi and Mj are associated with I and J. The splitting energy of the atomic terms under the push and back effect can now be written as. So it involves, that is the push and back effect, that is the hyperfine structure in the push and back effect, that is under the application of strong magnetic field, will consist of three terms, which I am going to discuss one by one. The first term is this one, Gj, mu b, mj, and b naught. This is the splitting energy under the Zeeman effect without hyperfine structure. You know that there is no quantity like Mi. Mi is not present. That is, this quantity is independent of nuclear spin. So you see that it is associated simply with the Zeeman effect without hyperfine structure, because we are not involving a nuclear spin in this quantity. Now consider nuclear spin I. Each such level will split into 2i plus 1 hyperfine levels corresponding to Mi, where Mi is equal to I minus 1, I minus 2, and so on up to minus I. Provided Mi, that is I, is not an integer. If I is an integer, then Mi will be equal to 0 plus minus 1 plus minus 2 plus minus 3 and so on up to plus minus I. But if I is not an integer, then you will write Mi is equal to I minus 1, I minus 2 and so on up to minus I. And you see that here I have explained that if you consider the nuclear spin I, then each of these levels defined by normal Zeeman effect, which is Gj, mu b, mj, p naught, each of such levels will split into 2i plus 1 hyperfine levels corresponding to the magnetic spin quantum number Mi. The magnitude of the second splitting, you know that first splitting is because of the Zeeman effect, and the second splitting is because when we are considering the nuclear spin. So the magnitude of the second spin can be calculated using the vector model, which I am not presenting over here. I am just borrowing a result from the vector model, and that gives me the second splitting energy equal to A into Mi into Mj, where A is the hyperfine constant defined in equation number 37. A is equal to Gi into mu n into Bj divided by the square root of j into j plus 1. And Mi is the magnetic quantum number due to spin, and Mj is the magnetic quantum number due to total angular momentum J. So this quantity A into Mi into Mj will form the second splitting term, where the hyperfine constant A is given by equation number 37. If B naught is strong enough, the effect of B naught on the nucleus is not negligible compared to the field of the shells Bj. Even the value of a B naught will be small in comparison with the value of Bj, but even this small value will have some effect on the nucleus, and its effect will not be negligible even compared to the field of the shells, which is Bj. The Zeeman energy of the nucleus, that is the hyperfine Zeeman energy, will be equal to minus Gi into mu n into Mi into B naught. So this must be included as the third term. So the splitting energy under strong magnetic field is given by, so EHFS is equal to first term, which I have written over here. This is the first term. This is the second term. And then this is the third term, which is with the negative sign. So I have written all these three terms in equation number 38. So this equation number 38, I have written it as delta E, hyperfine structural splitting energy. Delta E is equal to this quantity on the right hand side of equation number 38. If you want to write this equation more precisely, you can write delta E is and you can replace mj as a delta mj, mi as a delta mi, like this. And when I shall explain this energy delta E from some spectra, then of course the things will become more clear. The transition region from strong to weak magnetic field is difficult to determine. So it is hard to determine the separation that at what level we go from weak to strong. So this boundary cannot is hard to determine. Terms in the weak, intermediate, and strong field range, and the strong field range from a state with the quantum numbers j is equal to 3 by 2 and I is equal to 3 by 2 are given on the next page. So you see that here I am considering two values of the quantum numbers. One is j is equal to 3 by 2. This is the total quantum number of the electronic system, and I is equal to 3 by 2 is the spin quantum number of the nucleus. So I am taking these two in order to explain the different energy levels. In case of weak, in case of no magnetic field, in case of moderate magnetic field, moderate mean weak magnetic field, and in case of strong magnetic field, V naught. So let me explain these first. So I have a level 2p3 half because the value of j is equal to 3 half, and I have the total spin I is equal to 3 half. From this is the nuclear spin. So from the j value I have j is equal to 3 by 2, and from the nuclear spin I have the value 3 by 2, I is equal to 3 by 2. So if you want to construct f from these two values, so you can write f is equal to mod of j value plus minus I value. J value is equal to 3 by 2. I value is, if you plus it with I value, which is 3 by 2, then it becomes 3. So the maximum value of f will be equal to 3. And if you subtract the j value from the I value, then 3 by 2 minus 3 by 2 is equal to 0, which I have written as the lowest value of f over here. This is the lowest value of f. And you know that when we write the values, we write all the values from the maximum to the minimum. So the maximum value is 3, the minimum value is 0. The other integer values between 3 and 0 are 2 and 1. So I have written all possible values of f, which are 3, 2, 1, 0. And this is in the presence of no magnetic field. And the splitting of these levels, which is equal to 3a, 2a and a, these can be calculated from the energy formula, which I have discussed before for the case of hyperfine structure, simple hyperfine structure without the application of the magnetic field. This is what I have discussed, those energy terms in lecture 1 or lecture number 2 of this series. Now you see that I am going to apply the weak magnetic field. So when you apply the weak magnetic field to these levels, which are the degenerate levels, so f is equal to 3 level is the degenerate level, f is equal to 2 level is the degenerate level, f is equal to 1 is the degenerate level, and f is equal to 0 is also a degenerate level. So if you apply the magnetic field, then of course corresponding to 3 you have, since 3 is an integer, so corresponding to 3 you have the magnetic quantum numbers 0 plus minus 1 plus minus 2 and plus minus 3. And I have arranged these 7 quantum numbers in the order of energies. So highest energy is mf is equal to plus 3, then mf is equal to plus 2, plus 1, 0, minus 1, minus 2, and minus 3. And similarly, corresponding to the value of quantum number f is equal to 2, the value of quantum number mf will be equal to 0, plus minus 1, plus minus 2. So these 5 levels have been written against the level f is equal to 2. And when f is equal to 1, then mf will be equal to 0 plus minus 1. So there will be 3 levels. And when f is equal to 0, mf will also be equal to 0. So you see that these are the possible levels under the application of the moderate magnetic field. And these levels are called hyperfine Zeeman levels. Now you see that I am going to apply the strong magnetic field. So under the application of the strong magnetic field, you know that the coupling between J, which is 3 by 2, and I, which is also 3 by 2, the coupling between I and J breaks down. So there will be no total F. When there is no total F, there will be no MF. And of course, these splittings, which are the hyperfine Zeeman splitting, will also break down. But you know that I have kept these splitting so that I can explain the push and back splitting out of these. And these energy levels due to push and back effect are shown with the quantum number mj and quantum number mi. Since you see that I is equal to 3 by 2, so mi will be equal to plus minus 3 by 2 and plus minus half. These four values will appear against each level. And since j value is 3 by 2, which can be inferred from 2p 3 half, so j value is equal to 3 half, and mj will be equal to plus minus 3 half and plus minus half. And you know that I have written plus 3 half, plus 1 half, then I have written minus 1 half and minus 3 half. If you want to if you want to study in detail the push and back effect, which I have covered in one of the previous lectures, you should consult those lectures first, in which I have discussed the Zeeman effect without incorporating nuclear spin, and the push and back effect, which was the simple push and back effect without the incorporation of the nuclear spin. You can consider those effects there, and you can easily understand why I have the quantum number mj and mi over here. So you see that these are the splittings, all these four levels corresponding to mj is equal to plus 3 half, and mi is equal to plus 3 half, plus 1 half, minus 1 half, minus 3 half. All these four levels will be split by the same separation, which is 3a by 2. And you can put the value of mj, mi, and into one of the previous formulas, and you can calculate the splitting between them, which is 3a by 2 for all these four levels. Similarly, the splitting between the intermediate levels is also a by 2 between all levels. So a by 2 is the splitting between these levels. Similarly, a by 2 is the splitting between these levels. And then, of course, I have the last level corresponding to mj is equal to minus 3 by 2, and mi is again plus minus 3 by 2 and plus minus half. And I have written these four levels are also separated by the same magnitude as the upper four levels, with a separation of 3a by 2. So you see that in the push and back effect, I have to rearrange the lines over here. You can see this green line corresponding to mf is equal to minus 1 of the hyper-Zeeman effect will be at the lower end. And then you see that other levels you can also see that are going at different positions. There is no way to explain why these are going over there, but you have to follow them because they satisfy the experimental data. So the hyperfine Zeeman levels can be associated differently so that you can obtain the data which is satisfactory with respect to the experimental point of view. So arranging this data in this way, and you see that here we have the same values of energy, minus 3 by 2, minus half, plus half, and then plus 3 by 2. And we have also arranged, you see that mi values differently for the lower two sets in comparison with the above two sets which have the same values. The lower two sets with respect to mi have inverted values of have values in inverted order, and also the values of mj. So you see that this explains the push and back effect. The levels and the splitting in the push and back effect can be explained by the quantum numbers mj and mi written with the orders with the same orders for the top two, and the inverted order for the lower two. And these have been arranged in energy wise. Their energies can be confirmed from this formula. So if you put the values of mi, mj, mu, n, g, I, g, j, and the value of a, which is the hyperfine constant. If you put all these values over there, then of course the value of delta E can be found to be equal to 3a by 2 for these well separated levels, and a by 2 for these narrowly separated levels. So you see that here in this figure, by taking the value of J is equal to 3 by 2 and the nuclear spin equal to 3 by 2, I have explained hyperfine structure up to the value of F with no B, with B naught is equal to 0. Then I have explained the with moderate magnetic field, I have explained the splitting of the hyperfine Zeeman levels. And then with the strong magnetic field, I have explained the push and back levels, hyperfine push and back levels under the application of strong magnetic field. Electron G factor, which we call as Gj, is taken as negative because Gs and Gl are also negative quantities when dealt separately, because the electronic angular momenta, which are the S spin angular momenta and orbital angular momenta S and L, are directed opposite to spin magnetic moment mu S and orbital magnetic moment mu L. So S and L, as we have learned from the previous lectures, that S and L are oppositely directed to the spin magnetic moment mu S and orbital magnetic moment mu L. Be careful when ordering different levels with different possible values of Mi. If Bj is greater than B naught, the energies of the nuclear states depend on the orientation of the nucleus with respect to electron. Quantum numbers are referred to B naught, which are not the same for all states as in case of Bj. So in case of Bj, the quantum numbers will be the same, but when we apply B naught, the quantum numbers may not be the same for all the states. So we have to be very careful when we are labeling the levels. Splitting of the ground state of hydrogen atom. Now you see that in the next topic is that I am going to explain the splitting of the ground states of the hydrogen atom. And you know that the hydrogen atom with one proton is also referred to as the protium, having only one proton and only one electron around that. So splitting of the ground state of the hydrogen atom in a strong magnetic field B naught is shown on the next page, which is this one. So you see that this is one. So let me explain. Here I applied the magnetic field B naught. And you know that this is a strong magnetic field. So you see that this is the Zeeman energy levels of the electron with the values equal to plus half into G into mu B into B naught. There is no quantity from the nuclear side which is involved over here. That is, I is not present, Mi is not present. So this is totally relevant with the electron. So this is the energy, Zeeman energy level of the electron. This is also the lower value of the Zeeman energy level of the electrons. And you know that when there is a transition between these two levels, there will be only one magnetic dipole transition between the Zeeman energy levels of the electron. You know that here I have specified the energy as plus G mu B ms B naught. Here I have used ms instead of mg, because if you are considering hydrogen atom which has only one electron, and if you are considering that electron in the ground state, which is called the s electron, for the s electron the orbital quantum number L is equal to 0. So ml will also be equal to 0. When there is no L, when there is no ml, only the spin will exist, and the spin quantity S is equal to half, and ms will exist there. only for the case of the hydrogen atom. So for the case of hydrogen atom, I can replace Mj by Ms, which I have shown over here. The rest of the quantities are the same. And here you can represent G by Gs because only spin will contribute in the Zeeman energy of the electrons. Because the orbital quantities for the s electron of the hydrogen atom in its ground state will be equal to 0. So this G can be considered as Gs and M will be considered as Ms. So Ms will have only two values, plus minus half. So you see that here I have used plus half, here I have used minus half. These are the values of Ms. And I have shown these two levels separated from each other. So when there is a transition between the upper level to the lower level, that is called a magnetic dipole transition. And this will be a single transition only. A single wavelength will be observed. Now the next I am going to discuss the hyperfine interaction of the nuclear electron. That is, I am going to discuss the nuclear spin over here. I am not applying. So you see that here I am going to discuss the nuclear spin, and the energy is of the nuclear, when we consider the nuclear spin, will be equal to A times Mi and Ms. Again, I have replaced Mj by Ms value. The reason is what I have explained, because I am considering the s electron of the hydrogen atom, for which Ml will be equal to 0 and only Ms would exist with the two values plus minus half. So this is the hyperfine interaction of the nucleus and the electron, which is given by the formula A into A into Mi and Ms. And if you substitute these values in one of the previous formulas in which I have calculated, I have given a formula for the calculation of hyperfine splitting energy, then you will find that this level will have a separation from this reference level by plus A by 4, and the lower one will be minus A by 4. And similarly for the lower Zeeman level, the splitting will be with the two levels with the separation with the plus A by 4 and minus A by 4. And then you know that next is the case of nuclear Zeeman energy. Here you see that I have a minus Gi, which is the G factor of the nuclear spin or of the nucleus, mu n nuclear magneton, Mi magnetic quantum number due to nuclear spin, and B naught is the applied magnetic field. And so if you apply this magnetic field, you will get okay, so you see that this is the splitting which I have shown over here for the case of the nuclear Zeeman energy. And you know that this will now be determined by two quantum numbers, Mj. Mj has been replaced by Ms. The reason is what I have already given. So I have the two quantum numbers Mj and Mi. Again, Mj is replaced by Ms over here. And you know that Ms has only two values, plus minus half. So plus half with the upper two levels and minus half with the lower two levels. And Mi, you know that in this case the value of Mi nuclear spin is half for the hydrogen atom. If you are considering hydrogen atom in its ground state, the value of capital I will be equal to half. So Mi will be equal to plus minus half. So plus half, minus half, minus half, plus half. Because this is actually the push and back effect. So you can consider these energies as the energies under strong magnetic field. And you can consider these energies as the hyperfine push and back levels. So I think that I have mistakenly written over here as nuclear Zeeman energy levels. You may call it as nuclear hyperfine energy levels. So please make a correction over here. These are the nuclear hyperfine energy levels. because in this energy levels only the levels and the positioning of these levels will be determined by the two quantum numbers mj and mi. Here mj has been replaced by ms, and I have written the values of ms, which is the plus values I have written for the first two levels, then minus half values, and then mi has written as plus value, then minus value, and plus value. And I have arranged these levels. You see that these values, for example, green is plus half, I have written as plus half also over here. But since there is a negative sign, you see that over here with this energy term. So this energy term, the negative sign will be multiplied, and then this half, which is mi, will be multiplied by the negative sign. This minus half will be multiplied by the negative sign, will be written as plus half. This minus half again will be multiplied by the negative sign in the energy formula, and you will get plus half. Similarly, this plus half will be multiplied by the negative sign, and you will get minus half. And this negative sign is over here with the minus gi into mu n into mi into b naught. So you see that these are the push back energy levels. Or you can say that these are the nuclear push and back energy levels, or the hyperfine push and back levels. And these levels you see that have been shown, these are the 4 levels in the number. And you can see that there are 2 transitions between these levels, because these transitions must satisfy the selection rules, for which mi is equal to plus minus half, and ms is also equal to plus minus half, sorry, plus minus 1. Mi is also equal to plus minus 1. And you know that I have shown these 2 transitions following the selection rules, that ms is equal to plus minus 1, ms is equal to plus minus 1, and mi is also equal to plus minus 1. Following these 2 rules, I have seen that there are 2 transitions, 2 magnetic dipole transitions are possible, and I have shown these transitions also. These are the magnetic dipole transitions, and you can see the separation A between these 2 transition peaks, whereas it was only one transition in the transition between the 2 energy levels of the simple Zeeman effect. This is a simple Zeeman effect, and this is the transition between the 2 levels of the hyperfine push and back effect. So two magnetic dipole transitions will exist following the selection rule, that mi and ms is equal to 0 plus minus 1. So you see that this is the picture which belongs to the ground states of the hydrogen atom. So you see that, let me go. I have explained the spectrum very clearly. Now I am going through these 2 paragraphs very quickly. Splitting of the ground states of the hydrogen atom in a strong magnetic field B naught is shown. The magnetic dipole transitions, which are observable by the electron spin resonance, are indicated. You see that here I am using the word electron spin, because in these transitions the spin is reversed. For example, from this level, which is a plus half, to this ground level, which is ms minus half. So the transition is ms plus half to ms minus half. So the spin flips over. So it is called the electron spin resonance. Similarly, consider this transition. For this transition, ms is equal to plus half, and the lower level has ms is equal to minus half. Again, there is a flipping of the spin. So that is why these are called electron spin resonance. Though these 2 transitions are called electron spin resonances. The magnetic dipole transitions which are observable by electron spin resonance are indicated. A single resonance frequency for the free electron, a single resonance frequency for the free electron becomes 2 transitions. You see that before that there was a single frequency, Single transition, single frequency. Now here there are two transitions, two frequencies. So a single resonance frequency for the free electron becomes two transitions in hydrogen atom due to hyperfine and Zeeman interactions with the proton. Their splitting corresponds to about 0.05 Tesla or 500 Gauss. The electron experiences a field of 500 Gauss from the proton. The nucleus is subjected to a field of the order of 0.05 times the ratio of the electron magnetic moment to the proton magnetic moment. And if you insert their values from the table, you will compute this value to be equal to 30 Tesla. So the nucleus is subject to a field of the order of 30 Tesla, whereas their splitting corresponds to 0.05 Tesla. The electron experiences a field of only 0.05 Tesla from the proton, whereas the nucleus will be subjected to this huge magnetic field. And you know that electron spin resonance is what I have explained between the two magnetic dipole transitions, because there the spins will flip when the transitions occurs. The electron spin resonance of the free hydrogen atom is difficult to observe in gaseous phase due to thermal motion of the atoms and their low density. Hydrogen atoms stored in alkali halide crystals can be used to obtain electron spin spectrum of the deuterium. Now this is the plot of the electron spin resonance of the hydrogen atom. The hydrogen atom may contain protium or the deuterium. So in the presence of these two, I have given you this plot, which is the plot of the electron spin resonance in the presence of the hydrogen atom as protium and hydrogen atom as deuterium. And you can notice that on the horizontal axis, I am increasing the applied magnetic field in Tesla. And the separation between these two extreme peaks corresponding to the protium is Mi is equal to plus half and Mi is equal to minus half, where A prime is the separation between these two levels. And also I am showing the deuterium and the separation between deuterium. There are three patterns due to the deuterium, and I am showing you the separation between them, which is represented again as A prime of 2H and A prime of 2H. And here because for the deuterium, the value of the spin quantum number is I. Nuclear spin quantum number I is equal to 1. So Mi will be equal to 0 plus minus 1, and I have shown these values 0 and plus minus 1 for the deuterium, whereas you can see for the protium hydrogen only Mi is equal to plus half and Mi is equal to minus half are present, because the value of the spin, nuclear spin for the protium will be equal to I is equal to half and Mi will be equal to plus minus half. Electron spin spectrum of the hydrogen atoms stored in the interstitial sites in the potassium chloride crystal is given and have been partially explained. The two outer groups of lines belong to the transitions with the delta ms is equal to 1 and ml is equal to plus half and ml is equal to minus half of the light isotope or the protium. That is the two outer groups which I have explained, that these are the two outer group. One outer group is over here, the other outer group is over here, corresponding to Mi is equal to minus half and Mi is equal to plus half. And you know that the transitions which are over here, the transition peaks are shown over here, and these transition peaks are due to delta ms is equal to 1, because for the hydrogen atom I should write delta mj, but since I have explained earlier that this is for the s electron where the ml with the orbital quantum number is 0, so I am writing it as delta ms. Otherwise you can write it as delta mg. So for the protium, I have written delta ms is equal to 1, mi is equal to half, mj is equal to minus half for the protium, having a splitting of 500 gas. Each of these transitions is split into 13 equidistant lines due to hyperfine structure, due to super hyperfine structure. We have called it as a super hyperfine structures because here the hydrogen atoms are stored in the interstitial sites in the potassium chloride crystal. And there is also an effect of the chloride ions from the potassium crystallite crystals, which is what I am going to address in this paragraph. This is due to the interaction with the nuclear moments of the four nearest neighbors of chloride anions with I is equal to 3 by 2. The chloride anions have a value of I is equal to 3 by 2. And there could be also an interaction from these nuclear moments of the four nearest neighbor chloride anions. The three inner groups of lines belong to the transitions with the delta ms is equal to 1 and ml is equal to 0 and plus minus 1 of a heavy hydrogen, which we call deuterium in this case, with the I is equal to 1. For the deuterium, we have I is equal to 1 and Gi is equal to 0.857. So putting these values, you can compute the separation between these lines also. The splitting constant A prime for the deuterium is smaller by a ratio of GI factor than the separation for the protium, for the lines for the electron spin lines from the protium. In the limiting case of the strong external magnetic field B naught, the hyperfine coupling of constant A prime measured by this method is identical to the isotropic hyperfine constant A as shown for the spectrum on figure number 25. So you see that this is the end of lecture number 3 of this series, that is the hyperfine structure. And I think that there will be at least one more lecture about the hyperfine structure of the nuclear hyperfine structure. So this is the end of slide number 17C of the course on atomic and molecular physics. And the lecture is still continued, and there will be at least one more lecture of this series, that is for the series on nuclear hyperfine structure.